So first thing Metro Ethernet people did was to define these services that we saw. So at least you can sell something. But in addition to selling something, you need to be able to guarantee and measure that you have met the guarantee. And that requires OAM. OAM in the carrier world, people in the data world, like people in the universities, have not heard of the word OAM. We don't teach you OAM here. We are really purely data oriented, but the people in the carrier world, people, telephone company people, they use OAM. OAM is operation, administration, and maintenance. So there are special frames, special protocols just for OAM. So IEEE went ahead and defined some OAM protocols. They are in 802.1AG, 802.3AH, and ITU has its own 1731. Actually, ITU is the telecommunication union, which means it's the telephone companies union. So they have lots of OAM protocols. 50 years ago, they started defining it whenever they started. So those are, they are full of OAM. IEEE is learning. Okay, so they define these. So first thing you need to define is the maintenance endpoints, MEPs. So here is a typical circuit: subscriber with a UNI to a UNI connected to a wholesale service provider with a ENNI connected to a service provider with a UNI connected to a subscriber. So this is assuming this is the same subscriber, two buildings of the same company. Subscriber cares for performance from here to there. That is called subscriber MEG, maintenance entity group. That is the level of administration. Subscriber really cares for the performance from here to there. If you have one office in St. Louis and one in Kansas City, you care for the whole end-to-end. Right? However, your endpoints are up to here, basically in your home, in your buildings, but the carrier cannot guarantee that inside your home. They will just guarantee up to the UNI. Okay, we talked about UNI last time, that there is a plug outside your home, which is the AT&T's UNI, and they will come and check that you're getting service there and how you're getting the service, when it is down and all that. That is their responsibility. So from this triangle, MEP, endpoint, all the way up to here, they will keep track of and check it out that there is no problem on their side. Okay? And then they could have some MIPs, intermediate points, where, they're not guaranteeing you anything, but they could still find out, where the things are, if there's something is wrong. But the endpoints are important because that is where the guarantees are. And the service provider is using other service providers. So for example, this is your carrier, but they are using this wholesale service provider. So they want guarantees from them as well. So this wholesale service provider has its MEG. And it has its own intermediate points. And this one has its own also, just to be sure. And so there are many MEGs, MEPs, and MIPs. One more time. MEG is what you are interested in. MEP is where it is measured. And MIP is where else it could be measured. Okay? Now, if suppose a link is broken, you can't get the packet through, then obviously lots of ping packets will be sent, and we will figure it out that the link is broken between these 2 points or these 2 points. Then we can go and fix it. Right? So it's important to know where the MIPs are, because they help you diagnose. All right. So Metro Ethernet people defined some OAMs. So first set of OAMs is for performance monitoring. Remember, OAM is three things: operation, administration, and maintenance. And so performance monitoring is actually there is a whole set of things that they guys do, but here we have just put two things here: performance monitoring and CFM, the connectivity fault management. So performance monitoring is just to measure throughput and latency. Okay, so there are some frames that are basically you can use and which are defined by ITU, and then you can measure what is the delay latency between different points. Okay, then for connectivity fault management is basically figuring out which link is down or where the equipment is down, and that could be service fault management or link fault management. Links are obviously the wires and the service is the equipment, right? And so for that there are special frames. If you go to this standard, there are special frames, but they are nothing but ping packets, except that ping is IP level concept, right? If you say ping, you go from a router to router to router, right? This is not called ping because the word ping is already taken. But the same functionality, if you do on the Ethernet, where you send an Ethernet frame and you get it back, that is called continuity check message, CCM. Alright, CCM is simply sending an Ethernet frame to some destination address and getting back from that destination address a response that I got it. That is a CCM. Everybody knows ping, right? Right, so this is CCM is at the layer below. Second thing is link trace message, which is nothing but your trace IP trace route. Some of you have sent the trace route. When something is not working, you send a trace route, and you figure out every router along the way will send you back saying that okay, I got it, and you can figure out where the packet is going. Right? Similar concept when you do it at the Ethernet level without using any IP. Remember, IEEE guys don't want to use IP. They cannot use IP. You know why? Because they're designing things that can work at the Ethernet level. Right? They are only responsible for Ethernet. They're not responsible for anything higher. So they cannot use anything higher. They have to make everything work at the Ethernet level. And who knows what is going on Ethernet? Maybe it is IP, maybe it is not IP. So they cannot define based upon that the payload is IP and therefore we can send you a ping. So they have to design everything. So they repeated the whole trace route message. And that is called link trace message. LTM. And the LTM, whenever it goes to any switch, now remember, any switch, it is reflected back to the source. And that is called LTR. LTR is link trace response. So you get lots of LTRs for your one LTM message. And so with this method, what can you figure out? Where the link is broken. Right? This is your connectivity fault management, CFM. So there are two special frames. So basically if you go to the standards, which were mentioned in the previous slide, they will tell you what the fields should be in those frames and how you should respond and things like that. We don't want to go into that detail. As long as you know that there is a message there, somebody who is implementing it will implement it. If you have to implement it, of course you have to read the standard. Right? So everybody understands the OAM which has been added to Ethernet now? And of course, everything that we are saying for the carriers, can you use it in the data center? Right, because if something is broken, you don't know why it's broken, you just send an LTM and you get an LTR back, and you can do that. So that's why we are teaching you all this. All right, any question about OAM?
This is the maintenance part, so specifically because this is the maintenance.
Right, good point. So I haven't talked about administration. Administration is more like management, and similarly, so there is a whole management set of frames, which actually turns out we did have. So Ethernet does have management frames. So that is nothing new. Everything in the networking that is designed has something called MIB, Management Information Base. And so every device in the data world as well as in the carrier world has a MIB, and all you need is a protocol which is SNMP or something like that. You send a message saying that, okay, tell me how many packets have you forwarded, and the MIB will, and the router will tell you, okay, we have forwarded 2,000 packets. So that management part is all set. That's why we haven't talked about. There's nothing new there. What was not there, this maintenance part. Okay, any other comment or question? All right. So we go to use cases. This is just an example how one can use Ethernet services. So let's say you are company X, Bank of America, my favorite example, and you have 2 buildings. Obviously, you have 2,000 buildings, and then you also want to be able to connect to the internet. You go to the carrier, and you say that I need, in this case, I need 2 EVCs. One goes to Kansas City, one goes to the internet. Right? And if it so happens this service provider actually, I gave you an example of Kansas City, but generally, if you want to really go to Kansas City, I think you will end up going to 2 providers, because there are city providers, metro providers, there are intercity providers, and so on and so forth. So there is a whole set of carriers that you have to go through. But that will be responsibility of your local provider. All right, you really don't know when you make a call from here to Germany, you don't know how many carriers you are going through and who is paying for them. You just pay one bill to AT&T or whoever, and then they pay the rest of the bills. Right? So assuming that this is one carrier, these are the 2 ECs these are the 2 EVCs, virtual circuits you will need, and that's it, done. The main thing to notice is that I put here ENNI because it is going to the internet, not to a particular subscriber. That is going to the world. So probably going to some carrier which take up from there. And then let's say you want to go to the cloud service provider, you want to connect to Amazon, and so here is the Bank of America, here is the WashU. They both want to connect to, let's say, Amazon. Then what they will do is they will set up a EVC. Actually, Amazon probably will set up this for you. So they will set up an EVC to one customer and to the other customers, and all of these will go over one wire. So here is the interesting thing is that Amazon is not going to have one wire per customer. They are going to have one thick fiber, actually not thick fiber, thin fiber, because the fiber thinner is better, by the way. So they will have one fiber that will carry all their customers to their building. Right? And virtually in that physical fiber, virtually there will be many circuits. So that's why they are EVCs, and they will have an ENNI. So they can receive all these multiple EVCs in one interface. Just like a carrier, they will have an ENNI. All right, and so both of these will go. Now this EVC consists of one OVC, second OVC. This one consists of one OVC, second OVC. Each EVC consists of multiple OVCs. This is what we taught last time. Right? So that is the carrier's responsibility to set all that up. And then we are done. I think the key point to notice on this slide is that if you are a big customer, you can get ENNI.
So this use case actually is for a big customer, because a small user can use through internet, Amazon's EC3, EC2.
Right. You don't need dedicated. But if you are Bank of America, you need dedicated. I mean, I'm just saying most of the enterprises, if they're really relying on the cloud, they cannot just use the internet as it is. It's like this. When we go from this campus to the medical campus, we cannot just go through the internet as it is. We need a dedicated line. I mean, when I say dedicated, I mean a virtual dedicated line. Okay? Any question about these examples? By the way, next Monday is the exam. So just make sure that if you have any questions, this is the time to ask. All right. Ethernet provider bridge. So now the Ethernet is getting into the business, the IEEE actually is getting into the business of somehow fixing Ethernet so that the carriers can use it. First came MPLS, they fixed IP, they fixed MPLS, so that carriers started buying MPLS rather than SONET, which was their favorite. Right? And then the Ethernet guys said, why do we need this MPLS? Why do we need IP? We can just do everything on the Ethernet itself. So they decided to design many things. Actually, the OAM was not the first thing they designed. They designed PB first. So let's see what is PB. PB is short form for provider bridge. Provider is carrier bridge. So basically, let's assume that there is a carrier and you have a building here and a building there and a building here and a building there and you want to connect. We saw this picture before. And so we have a carrier edge device, sorry, not carrier, customer edge device, CE, and this is provider edge device, and so on and so forth. The main problem, first problem that you run in is that if you have multiple customers, they are going to use the same VLAN numbers. I may have VLAN number 100, you may have the VLAN number 100. Now when we try to route the packets, we don't know who is 100 we have. Yeah.
So it's going to be silly questions, but may I ask, what is the difference between the CE and UNI?
Why the difference? Okay, all right. Okay, no. So the thing is, UNI is the interface, CE is a device. In between, if you draw a line there, that would be UNI. Okay. CE is a switch or a device or a router or something. PE is a switch or a device or a router or something. Okay. The connecting point between the two, there is an interface. So UNI is an interface. I for interface. This is E is for the edge and the device. Does that answer your question?
Actually, interface could be this is a device.
Interface is not a device. Interface is basically, if it is a device, then somebody has to own it. Interface is, okay, so let me explain an interface. Let's say I write a program, okay, which you are going to use. You will define an API. That is an interface. But it's not a program. I write a program, you write a program, and there's an API in between. Right? So that is, it's just, okay, so interface, let me give another example of interface. Interface that we use every day is Ethernet interface. When you take an Ethernet cable, and there are 8 wires in it, there is a interface defined which says the first wire should be this, second wire should be this, third wire should be this, the signal level should not be more than 200 volt, otherwise we will burn up, things like that. That is an interface. It's not a device. It's just a piece of paper which tells you what should be followed. All right, and the interface is basically those wires. Similarly, when you have a phone company, I already told you that the phone company has this RJ11 port outside. That's an interface. RJ11 belongs to them, but then the wires have a meaning.
But previously you told us like a uni is toolboxing an F1, right?
Okay, so okay. Hold on. If I said that, I probably simplified things a bit. Interface is a line. Now I'm simplifying it, I know, but it's a plane. I mean, it could be a line, it could be a plane, or whatever it is, dividing between the two, and then everything that crosses that line or a plane has some meaning defined. It's like an API.
Yeah.
Okay, next.
I was just going to say that the uni is just the demarcation point from the carrier. It can be a wire, a cord, some type of way where you can plug into the network. It's not a router or a switch.
Yeah, right. Device is yours. All right. So now we understand what is CE and PE. Now, second thing I will tell you what. There are two kinds of networking people. I have a good cartoon which is not here right now. One is called bell heads and one is called net heads. Bell heads work for the AT&T and for Bell Labs. They only think in terms of unis and things like that, right? And the net heads are people like us who work for the universities and teach data networking and actually work for Cisco and other companies that do data networking. We don't think in terms of interfaces. Even IEEE, you go ahead. I mean, now you'll hard to find words unis and things like that. We still use these CEPs, blah blah blah. So there is that difference too. ITU uses uni all the time, and they have it's like OAM. Now we are learning OAM. So the net heads are learning the bell. So what is happening? The two worlds are mixing now. So now the bell heads are learning about the net, and the net heads are learning about the bell. Okay. So that's the thing. You'll find that I may not be using a uni word here, but it has this is what the IEEE does too. All right. So now we need to let's back to the problem. The problem was that there are too many people using the same VLAN number, so we cannot distinguish with them. So there is a new standard called AD, 802.1 AD, which was done in 2005, and it's called Provider Bridge. And it's also called Q in Q, and that is a good name. Q in Q means that we have a VLAN inside a VLAN. Q is VLAN, right? 802.1Q is a VLAN standard. So Q in Q, this Q is not QUE, Q is VLAN. Q in Q is basically what happens is you put another VLAN on the front of it. So there is a customer VID, which is customer VLAN label or whatever that is. And this is the service VLAN or something. So instead of calling provider, they call it here service for whatever reason. So the service provider's VLAN. Service provider puts its own VLAN, and let's say it calls this one VLAN 1 and this one is VLAN 2. Now inside this VLAN are all the VLANs that are coming from customer B. All the packets actually that are coming from customer B. That could be some unmarked packets. That could be some tagged packets. That could be some other packets. All right, and similarly this one has another VLAN. So this solves several problems. Not only it solved the problem of keeping the customers separate, it also solved the problem of one customer's unknown packets going to the other customer's unknown packets. You see, unknown packets, we don't know who they belong to, and therefore we broadcast them, right? And if I send lots of unknowns, I could have a bug in my computer and generate lots of unknowns. Then I could affect you because you're using the same carrier. With this, everybody is kept separate on a separate VLAN inside the carrier. So when the packets enter this carrier right here, a new VLAN tag is added. When they get out, that VLAN tag is removed. Okay? So now you have two VLANs. One is the service provider's VLAN, which is called SVID. One is called carrier's VLAN, which is called CVID, and the numbers of the protocol type are 8100 and 88484. Now check in your handout, this number should be there. Okay? So this is called Q in Q, because we have two 822.1Q headers. Alright? Now you can have 4,000, you can have 4,024 VLAN. Service provider can have 4,024 and each customer can have 4,024. The total number of VLANs can be 4,000 times 4,000, which is 16 million. Any question? Yeah, we'll see in a minute. So can you do it 3 times? Yes, and I can do it. And they did it. But right now let's stay with 2. Okay? Now, that tag VLAN, service VLAN ID has basically is 12 bits. And then there are 4 bits in front of it, priority and CFI. Now these priority and CFI are not the customer priority or customer CFI. These are service providers priority and service. So you are a customer, Bank of America, and this is a customer, Jain. So AT&T will assign different priorities to the traffic. Right? And that is the priority put here in this tag. In the outer tag, the priority is the priority for the service provider. Right, which could be different from the customer's own priority. Depending upon how much you pay, you get higher priority. The whole thing is called S tag. So the tag means the whole thing, and VLAN ID is just part of it. 12 bits are called VLAN ID, and this whole thing is called S tag. It turns out this whole thing actually 16-bit plus 16-bit. Oftentimes we prefer to just indicate separately. So this is 16 bits plus 16-bit. Type is shown separately so that you can figure out what is next. So this is 16 bits right there. Out of that 16-bit, and we call it SVID, out of that 16-bit, 12 bits are really the VLAN ID. And then there are 4 bits which are priority and the CFI. Anybody remembers what is CFI? Anybody? Nobody remembers. Okay. All right. Canonical. Anything else? Canonical something? Makes sense to anybody? What does C stands for canonical? Alright, I covered that in this class actually. We covered it in 473, but I covered it in this class when we did the Ethernet fundamentals. So there was 2 kinds of addresses. First was Ethernet address, the IEEE 802.3 addresses, and there were 5 addresses, token ring addresses, and they were written differently. So they had canonical format indicator to indicate whether the address is in this format or that format. We no longer have token ring, and therefore all the addresses are canonical, so we use it for DEI, which is drop eligibility indicator. Right? So same thing here. That would be drop eligibility indicator. This is your priority, this is your drop eligibility indicator. And the priority could be strict priority or could be AF. Anybody remembers what AF stands for? Assured forwarding. This is why I taught you differentiated services. So assured forwarding kind of thing you could use, and here actually there is a mismatch because they talk about 6 AF. So whoever designed it didn't know that the AF is only 4. So it doesn't really matter. All it means is there are 6 classes, and they're not related. Right? There is no reason that AF1 or AF6 gets any better service than AF3 or AF4. They're just different queues. Right? So the number of classes is unimportant, but they call it AF here. All right. So we just finished a whole set of standards called provider bridge. And what provider bridge now allows is that it allows you to go over one carrier. All right. As soon as they started deploying this, they found out there is another problem. That you really don't go over one carrier, you need to go over multiple carriers, and when you go over multiple carriers, you run into another problem. So let's say you are here subscriber, you go over a provider, and then they go over a backbone which is somebody else. So this could be tier 3, this could be tier 2, somebody else. Now that somebody else has to remember everybody's addresses, because remember the forwarding is still by the source and destination addresses, and it has to be learned. So you have to find out where the packets are coming from, and remember all that, and then when some packets comes, you know where to send them. All right. So if this provider is serving 10,000 customers, 10,000, 10,000, 10,000 here, this is serving 40,000 customers. Each of them have 1,000 addresses. This guy is going crazy, trying to remember all those addresses and learning them and unlearning them. Right. So there were just too many MACs to learn and unlearn, and so they said, okay, all right, we will do all this job in big boxes which we'll put at the edge, but in the core we don't need to remember any of this. So they designed another standard which takes care of this large number of MAC addresses, and that is called MAC in MAC. So MAC in MAC, the name is on the next slide. Basically, this is 802.1 AS 2008, 5 years ago. And so what they did was they said we will take the packet that comes in. Right here we will decide where it is going, and rather than let everybody inside trying to figure that out, we will put the destination of the exit bridge. We will put the address of the exit bridge. That way the core can be simple. And core can go fast. Right? So here is the edge, here is the core, and the edge bridge still has to remember all the addresses. So when it sees a packet, it remembers it came from here, and when it sees a packet coming from here, it sees it coming from here, and then they exchange, and they know that when a packet is going to that address, it has to be sent to that bridge, and so they keep complete address list here in the edge. Those are big switches. Okay? But when the packet is sent inside, they put another address in front of it. So they have a BDA, BSA, and that is the bridge or backbone actually. Backbone destination address, backbone source address. So the core addresses only have to learn BDA and BSA. They have to know when the packet is going to BDA, how to send it. It's a smaller subset, very small subset actually. Backbone destination addresses. Only the backbone core only needs to learn about the backbone, the carrier's its own switches addresses and ports addresses, device addresses, and not the whole world. Now when we are adding the addresses, we might as well add a VID. So this is your third Q in Q you are talking about. So this is the backbone VLAN address. All right. Now when we are doing VLAN ID, we might as well put a fourth one, which we call service ID. What is service ID? So basically, the VLANs are set up by the carrier so that it can delimit its broadcasts. And just like we had pseudo wires inside MPLS, similarly, you could have pseudo wires. We won't call them pseudo wires because that word is taken up by IP. We call them service. So we can have service IDs, which are thin wires going through those big VLANs, and each thin wire serves a customer or serves a particular kind of traffic and serves a particular kind of VLAN, and we will define that more precisely in a minute. But every service has a packet which goes through a particular VLAN, and each VLAN could have hundreds of such service wires. and we won't call them wire yet because there is no really a wire. The packets are just connectionless. Wire means connection, by the way, in some sense. So anyway, service. So there are now 4 kinds of things. Now this is really not a queue, so I wouldn't call it queue because this is a service ID which is 32-bit long, whereas SV ID was 16-bit long. So we have a lot more bits here to indicate a service, and therefore it's a different type here. This is not a type which says that this is a LAN and this is a VLAN. This says this is a service. So this type indicates that this is a service and this is a service ID. All right, so let's just revise the whole thing. So this is what is this address? Backbone destination address. This is the backbone source address. This is the type, which is actually the same as here. So it doesn't really matter whether you have one more there or not. All we know is that this is simply a VLAN. So we look at the VLAN and then we forward, because all the core bridges forward based upon 2 things. They forward based upon the destination address and the VLAN. 60 bits. Alright? The same destination address on a different VLANs will take a different path. The same different destination address on the same VLAN may take a different path. So we need both the destination address and the VLAN to find out which port I should send it out. Okay? So those 3 things are used, VLAN ID and the destination address, 2 things are used to forward the packet. This is not used by the core at all. The core doesn't even look at the service or anything like that. And this is a standard Ethernet definition now, whether this is PBB bridge or whether it is a PB bridge or whether it is a customer bridge. Everybody does this. They just look at the destination address and the VLAN ID and they send the packet. That's the standard definition, standard thing. So this is nothing new. Now we have the service IDs. Service IDs, basically what it does is it allows you to somehow have in one VLAN many things that you can distinguish later on. And so it's the same concept that we had before. So what is a service? A service could be all frames coming on a specific port. Everybody coming through that door is one service, because that door goes to Bank of America. Okay? Or everybody coming on that door with a service VLAN of AT&T. So anybody who is coming through that door and came from AT&T, they have the service VLAN of AT&T. Remember that PB? That was called SVID. So if your SVID is 5, you go on this service. I mean, your service number is something. Or anybody coming from a specific port with a specific service LAN with a specific customer VLAN. Or we could go one more level inside the packet and see, okay, you have this service VLAN and you are coming from that customer of that carrier, you go on this wire. Okay, so we could go 3 levels deep and define a service. Here's an example. So if anybody who is coming on port 1 goes to SID1, and then anybody who comes on port 2 with VLAN 10, SVLAN 10 gets the service 20. Anybody who comes on port 2 with SVLAN 20 gets the service 33. Anybody who comes on port 2 with service VLAN 30 and the customer VLAN of 100 goes to port 401. Obviously, they could not be that you could put something that doesn't make sense. For example, if I put a 20 here, that doesn't make sense, because they would have gone to 33 and they would not even come to this line. Right? So here, the way I have prepared this table is so that these are all exclusive. So anyway, service 401, service 5, and then there is another table that the carrier prepares, which says that anybody going on service 1 should go on VLAN 1, anybody going on service 2 should go to VLAN 3, anybody going on 401 should go to VLAN 4, 502 should also go through VLAN 4, which I have shown by a figure here. So the traffic on port 2 is divided 3 ways. One of them goes to VLAN 4. Traffic coming on port 3 goes to VLAN 4 too. You can see two of the services are using the same VLAN. Alright, so now you see the need for a service. Basically, and the second thing is that there could be many services, because services could go all the way to the customers. So how many customers could we have? If you are a backbone, so you already have so many carrier customers of yours, and each of those carrier customers have their customers. So you could have lots of services here, and therefore services need 24 bits. Services need 24 bits, and so those 32-bit that you saw instead of 16-bit, now we extended it to 32-bit. Out of that, 24 bits are service ID, and then we have 8 bits left, which are defined as follows. First 3 bits are priority, and 1 bit is DI. This is how it was in the case of VLANs 2. We had 3 bits of priority and 1 bit of CFI or DEI. Then they added these more bits, and they didn't know what to do with these 3 bits, so they are reserved. But there is 1 bit which says use customer address. Okay, and this is generally used only in CFM. So when you want to do connectivity fault management, then you want to check how far your trace route is going, or how far is your ping is going. You can use that bit set, and it will go to that part, customer address as well. And then you have 24 bit of SID. Technically, this whole thing is called S-tag, and this is called I-tag, and it includes the customer destination address and the customer source address. So if you go back to the previous picture here, you see right next to the ISID is the customer destination address and the service source address. This whole thing is called I-tag, although none of it is used by the core, but in some of the OAM you might need that. Alright, so now let's see a pictorial one more time. So a service, multiple services could go through a VLAN. So this is a VLAN. Now notice VLANs don't have to be point to point. VLANs are virtual LANs. Just like a LAN, they could be point to multi-point. And so there it is. This is a VLAN. This whole thing is one VLAN. Right? In that we have 2 services going. One service is this orange or whatever color that is service, and that is SIDA, and then there is a blue service which is point to multi-point, and it's going that way. This is another VLAN, and it has 2 services going, both point to point. So you see the services themselves are like virtual private virtual LANs, and they could be inside another virtual LAN, which are the service providers virtual LANs. So this is backbone virtual LAN. So this is VLAN, means backbone virtual LAN, and this is the PBB core bridge. This is the PBB core bridge, and it doesn't need to look at the service ID. It doesn't look at the service ID. What it does is it looks at the VLAN ID. It looks at its own VLAN ID and the source and destination, and it sends the packet. Service is not looked at inside. Okay? Any questions about this? So what we have learned so far is what we call PBB, provider backbone bridging. So first was PB, provider bridging. Then was PBB, provider backbone bridging. Alright, MAC and MAC. Any question about these two before I go different topic here? So now we again went on to basically provider is still not very happy. And so we want to do something more to make them happy. And what they were not happy about was that they really are coming from a world which was connection oriented. Remember voice. Before you can speak a word, the connection is set up from here to there. And then when you get a dial, so basically what happens is when you pick up the phone, you get a dial tone, you put the number in, the connection is set up. When the connection is set up, then you can say hi, right? Before that, it doesn't go anywhere. So same thing they wanted with the Ethernet is that they wanted to have a connection set up. So there is something called connection-oriented Ethernet. Connection-oriented Ethernet, and the advantage of connection-oriented is that you can now guarantee, because I have set up the connection is set up at 100 megabit, you can send at 100 megabit, it will get to. If I don't set up a connection, if I do just what we call connectionless, then there might be a queue where it might run into and not get 100 megabit. With a connection-oriented, you have guaranteed reservation in every queue. So connection-oriented, the path is determined at provisioning. Provisioning could be done just by somebody sitting at a terminal and saying, set up a path from St. Louis to Kansas City, and it will stay for 3 months. Or it will stay for the whole year, it will stay until I disconnect it. And this is how you get a circuit from the phone company. You cannot just send a packet and say, okay, disconnect. You have to call the phone company and they set it up and you get the service. Your service starts tomorrow. And then when you call them and say, well, I want to disconnect it, they say, okay, all right, it will be disconnected on date such and such. Right, that is called provisioning. Yeah.
Connected-oriented Ethernet very similar to setting up like virtual circuits?
It is like setting up virtual circuit. Now, see, here is the difference. I mean, it will become clear in a minute. So let me answer that question after 2 slides. So, connection-oriented path determined at provisioning, path provisioned by management. See, this is the key that I wanted you to understand. Management means that we send a management packet, which means the AT&T that is managing their network. They could send a management packet to their PE, provider edge bridge, and say, look, set up a connection, set up a VLAN, or set up something, connection-oriented path between these two PBs. So they send a management frame as opposed to, so you can call it a virtual circuit, but it is not set up by normal thing like this setup is that this PE just sends a message saying that okay, set up a path. It is set up by the management, right? And therefore it has deterministic quality of service. There is no spanning tree, no MAC address learning. So none of those probabilistic things. With spanning tree, you don't know how your packets will go and where they will go. MAC address learning, same thing. Frames are forwarded based upon VLAN IDs and backbone bridge addresses. Path not determined by the customer MAC address and other customer fields, so it is more secure. Reserved bandwidth per EVC, and then you have bandwidth reserved. And pre-provision protection path. So you could even say that I want 2 circuits, one working and one protection. Okay. We are getting closer to what we call SONET. The key word in the carrier world is SONET. And they want everything that the SONET does. Alright, so we provide protection path. And that is called, and so actually first step would be without any standards, one could design a what we call VLAN Cross-Connect. A VLAN Cross-Connect is a device, not a network, where you could go from one port to the other port based upon VLAN ID. If you're coming on port 1 and your VLAN ID is 200, you go to the output port 7. If you're coming on port 2 and your VLAN ID is 201, you go to port 5, and so on and so forth. So this is just basically a device that anybody can. So somebody must have designed, some company must have designed the VLAN Cross-Connect, and so we have that thing here. It doesn't require any standardization. What does require standardization is what we call PBB-TE. So one step next. PBB we already learned. The next thing is PBB-TE. That is Provider Backbone Bridges with Traffic Engineering, and this was done in 2009. All right, and basically it provides a connection-oriented point-to-point Ethernet service. So this is not yet ELAN service; it is E-line service. And I have put the line in blue and italics so that we have no confusion whether I thought about it or not. It is a line, point to point. By the way, PBLS is a LAN service. So that part, last time we discussed there is LAN or line. That is LAN service. But this one is line service. So for PBB traffic VLANs, we turn off all MAC learning. We discard the frames with unknown addresses and broadcast, no flooding. And disable spanning tree protocol. All protection paths switched for each direction of the trunk, and so basically we add a protection path, not all, add protection path. So whatever we said in the last slide has been standardized, and the switch forwarding tables are administratively populated using management. And this is important, is that we don't learn the addresses anymore. We just fill in the table. Okay, and same frame format as MAC and MAC, no change. So the frame format is same as was in PBB, which was this frame format. This one. Frame format is all same, but we don't look at the edge bridges. Don't look at the customer addresses. Okay, it's all pre-provisioned. All right, no change. So quality of service, guaranteed quality of service, no need for MPLS or SONET SDH. Uni traffic is classified by the port with the service VLAN ID, customer VLAN ID, priority, unicast, multicast. All of these things are looked at. I mean, basically, and then put into the packet. Uni ports are policed. So just we saw those two leaky buckets. We use those two leaky buckets. Access traffic is dropped. Access means which is beyond the access itself, right? And no policing at the NNI port. So there is no policing in between. I mean, you cannot do policing from carrier to the next carrier, but you do the policing at the beginning. And so here is a total path from subscriber to a carrier to a carrier to a subscriber. Here we will do three things. We will do classification. This is what we do. We look at the port. We look at the service, we look at the VLAN ID, we look at the priority and whatnot, and whether it is unicast, multicast. All of that we looked at here. That is called classification. Policing, and we drop the packet, we mark them, and marking. Marking is marking that the EI bit if it is over the access. So all that is done at the beginning. In the intermediate point, all we do is scheduling and remarking. So it should be clear, scheduling is simply putting into the right queue. Remarking is in case we are getting into trouble, we can, I mean, this carrier actually has a contract with this carrier also, or this carrier has a contract with that carrier. Say, this is the maximum I will get is 100 megabit or 100 gigabit. And if you go over that, actually you will have 100 gigabit plus minus 1 gigabit or something. And if you go over that, then they will remark your packets. Yeah.
NNI is that was ENNI. So you
I use the word ENNI. I should put the ENNI here. So NNI, yeah, the difference between ENNI and NNI is network to network interface. And that word has been around for a long time. Right? When the Ethernet came in, that a special version of NNI is called ENNI. Ethernet NNI. All right? And, I mean, fortunately, they didn't call UNI, has been around for a long time too. They could have called it EUNI. Right? But that word they kept, UNI, but they changed that NNI to ENNI. Okay? So, if you like, you can just call this here ENNI.
What about the policy instead of ENNI?
Policing.
No, policy.
No policing at NNI port. So here you cannot put a leaky bucket. Okay, all right. So you are not really doing policing here, but you are remarking. Let me see. I think I said something which maybe have been wrong. Is that you do not put a leaky bucket here, but you are remarking because because if for some reason you find that the traffic is this is a good question as to how do you remark. It could be that you are just changing the priority, not really the drop bit. Okay, because if it is coming from somebody, their priority would be different from somebody else, and we could be just changing their priority bits, right? So I think that is what remarking means here. And shaping is that you can shape the traffic. What does shaping the traffic means? When the traffic comes, it comes in a very bursty manner. 1,000 packets show up at one time, and that's not very good. What we want is, if you want to send 1,000 packets and then 1 second later there will be another 1,000 packets, why don't you send those 1,000 packets every 10 millisecond? Well, every millisecond actually, so that they will be equally spaced, and then the next batch comes in, they will be equally spaced. That is called shaping. Shaping means making the traffic smooth. So that leaky bucket we showed you actually is a shaper too. That when it leaks one packet at a time or one frame at a time. First frame leaks and then you don't do anything, and then your second frame leaks after some time. So that's a shaper. All right, so let's see, let me just understand. Everybody understands what does classification mean? You look at the fields of the packets, some fields of the packet, and decide, well, this belongs to go to this particular flow. Everyone understands what policing means? Policing means that you measure and you discard the excess. Everyone understands what marking means? That we mark the priority and the DEI bit. Then shaping. Shaping means making the traffic smooth. All right, that brings us to almost the end. So basically, you see the evolution. Previously, the standard Ethernet was this form, where you had no VLANs, only the destination address and the source address. In 2005 or some time frame, they added, actually it was 2003, more like that, they added a VLAN tag in between. And then in 2007, 2 years later, they added a provider VLAN, which they call SVID. And sometimes I get confused because they use the word S here and they use the word provider, service provider. Okay? So they have SVLAN. And then few years later, they added PBB, which is they added backbone BID and then service ID. Okay, so the word S is confusing because here it is used for service, here it is used for service provider. I would think that if they would have called it provider PID, I would have been much happier. But anyway, that's how it is. So these are the things, and you can see the tag type. This is 8100, means original queue, and this one is 8808, which means that this is the queue in queue part. And this is service ID has 88C7. Okay. If you have to compare these technologies, you will find that basic Ethernet has no resilience. Resilience means if something goes, can you still survive? The answer is no. With MPLS, you can survive. With provider bridge, if you use the link aggregation or shortest path bridging, you can survive. With PBB-TE, you have protection and fast reroute. Okay. Security, there is no security. Here is circuit-based security. Here VLAN-based security. So somebody else's traffic cannot get into your VLAN. Here it is circuit-based. Nobody else's circuit can get into your circuit. You get a connection-oriented. Multicast is yes. inefficient in MPLS. It is there, but it is very difficult because everything is point to point. Here it is yes, here it is no. QoS is priority based, diff serve plus guaranteed, here diff serve plus guaranteed. Legacy services, now legacy service means T1 E1. Can you take T1 E1 over Ethernet? Well, yes, you can do it over MPLS, but not really over Ethernet. Because one thing we have not discussed is timing synchronization. T1 E1 needs very precise timing. So Ethernet is extending now, to make carrier happier, that is happening, but as described so far to you, we didn't talk about timing yet. Traffic engineering, no, yes, you can see, means guarantees. This is basically related to QoS. And then scalability, only 4,000 VLANs. Here it is complex. Here it is Q and Q. Here Q and Q and MAC and MAC. So you can really make big Ethernet networks. Cost is very low. It is medium here. OAM, there is no OAM in the original Ethernet, and there is good here. All right. So you can see how the technology has evolved to provide everything that the carriers wanted. And that brings us to the end of this module called Carrier Ethernet. To describe the Carrier Ethernet, actually we went into Carrier IP as well. MPLS is not Carrier Ethernet, that is Carrier IP, or Carrier MPLS if you want to call it. The reason we had to describe that so that you can see how the world evolved. Okay? So carrier networks are moving away from voice-oriented networks such as SDH, PDH to data-oriented networks such as MPLS and Ethernet. MPLS is very much in there. Ethernet is getting in. Okay, if you go to carrier network today, they're all MPLS, they're not all. Their MPLS is very much in there. They're mostly SONET with some MPLS, and Ethernet is getting in there. Ethernet over pseudo wires or MPLS is used to interconnect Ethernet switches over long distances. That is what first we talked about. Then the Metro Ethernet has defined EVPL, EVP LAN, and EVP tree, and EVP access services. Okay? Does anybody remember what is EVP tree? Huh? Private line.
EVCs.
Right here, tree. So actually I had another slide which probably didn't get in here. Let me explain why you need the tree. So the tree came in because lots of carriers, particularly wireless carriers, what they want is they have lots of towers all over the city, and they want to bring it to the main office. So what they need is a service that connects many points to one point. They don't need LAN. They don't need traffic one tower to go to another tower to another tower. They just want all the traffic to come to one place. So they requested IEEE, actually Metro Ethernet Forum, that we need this service called tree. So tree service is basically coming from the leaves to a root, and then from root to maybe one place else. So you could go to root, is basically central point, and then from there you can just go to your head office. So collecting the traffic from many places, and there are many other applications of the tree. The application of the tree is, for example, video distribution. If you are sending out video, like your television company or your Cox or whatever, you have one source and you are sending the same thing to everybody, right? So you need a tree, and there are other applications. So tree is that service. All right, access we talked about, the LAN and line. Then they had Q and Q and MAC and MAC extension. So now you understand what is Q and Q and what is MAC and MAC. Allows very large Ethernet networks spanning over several backbone carriers, and TE puts the connection-oriented stuff so that you get guarantees. Okay? Any question about the whole chapter? As usual, I have put the reading list, and this one says must read. Okay? So make sure you read that. Then there is a whole tutorial here which is very good. There is another tutorial which is very good, and there is a whole book which is very good. So, but whether you go to those or not, must read. Then there are lots of links for each individual topic, acronyms. All right.